Okay, thank you very much, Raman. So in this talk, I'll try to introduce very basic of the particle physics and try to, if time permits, try to go over a little bit some experimental facilities, a little bit introduction about experimental facilities. And we'll talk about a little bit about the muon. Okay, and yes, as Raman said, that nowadays in the high energy physics, it is we do not very often see new results because to see the new results, we need more and more high energy, and that becomes expensive and more technically challenged. So that's why we do not see many new results in the high energy physics so often. Okay, so so let's start with the matter. So we know that every matter is, okay, 1 minute. Okay, so we know that every matter is made up of molecules and fundamentally atoms in the ionized form. So these molecules are formed by chemical bonding of these ions. So basically, those chemical bonds, force involved in the chemical bonds is the electromagnetic force between the charged particles, charged ions. So these molecules are atoms, so they combine, they tie together, bound together to form the matter. So in forming matter in that level, the force involved is the electromagnetic force. So now the size of the atom is about 0.1 nanometer to 0.5 nanometer size of the atom. So if we want to see the atom, if I want to probe the atom, we need the light of wavelength of the order of smaller than the size of the atom. So atom is 0.1 nanometer, so we need at least 0.1 nanometer or smaller than that. Okay, 0.1 nanometer or smaller than that to probe this. But with the help of light, because the light wavelength is, if you consider red light, it is 700 nanometer. So by using the red light, we cannot, of course, probe. We cannot see inside the matter. We cannot see the atom. So we need something to create the wavelength, which wavelength is about 0.1 nanometer or smaller than that. So what we do in lab is we accelerate by using the electric and magnetic field. We accelerate electrons, either electrons or protons or maybe some other particles, small elementary particles. So as the quantum mechanics says that every particle has its wave nature also. So it is duality, dual nature, wave particle and the wave. So the wavelength of the matter is given by the de Broglie wavelength, which is lambda equal to h over p, where h is the Planck's constant and p is the momentum of this particle. So we can translate this momentum to the energy by using this relativistic equation. P and c is the equal speed of the light, m0 is the rest mass of this particle. So if I calculate and if I use the electron to probe the atom, to see the atom, the electron energy will be, so we need about kilo electron volt, maybe 1 kilo electron volt or something like that, in the order of that. So we probe, we accelerate the electron, hit the object with the electron, and we detect what is coming outside from this detects after the collision. We detect that information, and we analyze and we figure out what is the size. We can see the atom and molecules and their size inside, their size. So now let's go further back, further deep. Okay, so matter. So we saw that matter is basically made up of molecules, electromagnetic wave, electromagnetic force bound by, and the electromagnetism can be described by a set of 4 Maxwell equations. So these 4 Maxwell equations can explain all these phenomena in the electromagnetism. So this is very successful. So the 4 set of equations, and These four equations also show that if the electric field is oscillating electric field, it also gives the oscillating magnetic field, and oscillating magnetic and electric field gives the wave, which is called the electromagnetic wave, which speed is about 3 × 10⁸ meter per second, and which is the speed of the light. So we say that light is an electromagnetic wave. So this theory is the classical electrodynamics. That is the Maxwell equations, plus there is a contribution for the Lorentz also. So classical electrodynamics. And this is the first unified theory. Unified means, in this case, electricity and magnetism are combined together, unified. So this is the first successful unified theory, and it is a classical. However, there are some, this classical electrodynamics gives you the interaction between the charged particle. What will happen when they interact, push, pull, or if the charged particle is accelerating, it will radiate photon, radiation, accelerating or deaccelerating, absorb or radiate photon. So those all things are given by can be explained by the classical electrodynamics. But there are some problems with that. Classical electrodynamics cannot give the explanation of production or annihilation of the particle. So we can produce the particle. If I collide two particles, it produces many other kind of particles. Or if the particle and antiparticle comes together, they will annihilate and goes to the energy, photon. So classical electrodynamics cannot explain those things. So this needs to be modified. So with the development of the quantum mechanics is used in this classical electrodynamics. So that is basically called quantization. So the classical electrodynamics is quantized by using the quantum mechanics is using that. So it is a quantization of classical electrodynamic theory. So this and that theory name is called quantum electrodynamics, which is well tested and very, very successful theory, and developed by most 3 players on this development. Okay, so basically electromagnetic field is quantized by using the quantum mechanics. The quanta of the electromagnetic field, that is the smallest packet of the energy, that is the photon of the electromagnetic field. So photon is the force of the electromagnetic force carrier. So if we have a charged particle, they will interact. So basically they will interact via the exchange of the photon. Photon is going from one particle and absorbed by the another particle, and so on. So this is so force in quantum mechanics, quantum field theory, the force is always exchange force. So when there is a force, some particle need to be exchanged. So the exchange particle is the photon. One particle emits photon, another will absorb. So this is so electromagnetic interaction is mediated by the photon. So there is a medium, that is a photon. So we call force carrier of the electromagnetic force, yeah. So how does it look like annihilation? Annihilation, like if I take an electron and the electron has antiparticle. Antiparticle means same particle, simply charge is different. Charge is opposite charge. Mass is same, other things, spin and other quantum, other parameters are the same. Simply its charge is opposite. So this is called positron. And when the electron positron comes together, they will annihilate, and they produce the energy in the form of photon, that is 2 photon. It produces the 2 photon. Similarly, this opposite way, photon, it can decay to the positron and electron. That is called pair production. But here is when we do this kind of equation, just like in the chemistry, chemical bonding or chemical reaction, the charge must be same in the both sides, on the left and right side. So in this case, also charge must be same in the left and right. So photon has no charge, that is total charge is 0. There is other conservation law it need to follow. One is the charge Another is the energy conservation. So the photon will be produced so that the energy will be conserved. Another is the angular momentum conservation. Angular momentum on this side should be same as on this side. So here we have two particles. So there may be some angular momentum. And there is two photons. So there is some angular momentum. They can conserve the angular momentum. So this process can happen. Here, there is only one photon. So angular momentum is zero. There is two electron and positron, two particles. So there is some angular momentum. So angular momentum is not conserved. So directly this equation is not possible. It is possible in presence of atom or the nuclei. When this reaction happens, so photon is going, electron is going this way. If there is a nuclei nearby or the atom, then this it gives some amount of this angular momentum to this atom, so that the angular momentum will conserve. So this reaction happened, but in presence of the nuclei or atom. But this is happened. It's possible. Similarly, in case of muon, because we are talking about the muon, so mu plus, that is antiparticle of the muon, and this is the muon, which is negative charge, also decay annihilate to make two photons. So this annihilation and production, particle production is allowed in quantum electrodynamics, which is not possible in classical physics. In any classical physics, it is not possible. Now let's go further inside the atom. So we have atoms inside, outside, okay, electron. So now these electrons is bound with this proton inside the nucleus. So this is the electromagnetic force is involved basically. So electromagnetic force gives the size of the atom. Now let's go inside the nucleus. So inside the nucleus we have protons and neutrons. Protons have positive charge, so we know that positive charge repel each other, so they must go away. They repel each other. So if I apply the electricity, electromagnetism, classical, then this electron should repel each other and they move away, and there won't be nuclei, there won't be atom. Atom should not exist. So, but it exists, so it shows that there is some other kind of force other than electromagnetic force, which is bounding this proton inside it. And it is bounding against the repulsive force, electromagnetic repulsive force. So that force must be very stronger than the electromagnetic force. So that force is called nuclear force, which is bind this nuclei, proton, neutron, together. So the nuclear force. So experimentally, nuclear force looks like this. With this is the range, distance. So if size of the proton nucleon is about 1 Fermi, which is about 10 power minus 15 meter. So if we go close, if the nuclei go close to the another nuclei, first, okay, far away about 2.6, there is no force. You do not feel any force. But if you go, there is attractive force, because the force is attractive, negative force. But if it go very close, then there will be very hard repulsive force. So it shows that, okay, there is an attractive force, but they cannot be very close. If there is no repulsive force, then they will just merge, they will just fuse together, and there won't be any size of the nucleus. So basically, this repulsive force gives the size of the nucleus. So it keeps some separation between the nucleus. Nucleons. So within this range, there is very attractive force, and if it goes very close, then there is a repulsive force, and that repulsive force is responsible for the size of the nucleons, size of the nucleus. And first successful theory is given by the Ikawa, which is called Meson theory of this nuclear force. And he saw that this force, electromagnetic, this nuclear force is given by a kind of potential, V, which is of this shape, where R is the distance and G is some constant factor, and mu is the mass parameter. Now, mu is the mass parameter, if there is no mass, let's say for example mass equal to 0, then the V will be equal to G square over 4 pi and some 1 over R. 1 over R here, which is the same as the Coulomb's law. In the Coulomb's law, potential is some constant and the G over R, Q over R, sorry. So if the mu equal to 0, that's mass of the particle, exchange particle. Whenever there is a force, there is always some exchange particle. So if the mass of the exchange particle is 0, then it goes to the, if it is negative, it goes to the, convert to the Coulomb's law. So in the Coulomb's law, basically exchange particle is the photon. So photon has mass 0. But in case of nuclear force, it is very short range. Photon is infinite range. Electromagnetic force is infinite range. That means theoretically, two charged particles can exert force at infinite range. But this nuclear force is a finite range. It exists only within certain range only. So that short range is caused by the mass of this exchange particle, heavy mass of the exchange particle. So mu is the mass parameter, and because the exchange particle has some mass, heavy mass, so because of that, the force range is limited within certain range. So it is plotted here, distance. So this is the red is the Coulomb's law, Coulomb's potential, which goes infinite. And this Ikawa, that is the meson theory, there is a very attractive force, and after that, there is no force, almost 0. So after this, almost force equal to 0 here. So attractive will be within this region only. So it has certain short range force. It is a short range force. So basically, when two nuclei attract each other, when one nuclei is here, it's a proton and it's a neutron, or maybe proton or neutron. So let's say proton. So there is a attraction because of the nuclear force. That means there is exchange of the meson. And that meson later on discovered as a pi meson, pions. So it's called pions. So it comes in the pi plus, pi minus, and pi 0 also. The three shapes, three charges. So the nuclear interaction is mediated by pions, which is about 200 times heavier than the electrons. And pi 0 are discovered later. So pions, three charge, pi plus, pi minus, which is basically particle, antiparticle, and pi 0. Okay, so and later on it was found out that okay, so the Feynman diagram looks like this. Proton interact with the, let's say, nucleon, so they exchange pi 0, and proton goes here and neutron goes here. So the exchange is the pi 0 particle. They will exchange. So it turns out that later on that nuclear force will have a, let's say, proton here, and here is a proton. The force, repulsive attractive force because of the nuclear force, is actually the residue, only a residue, a small part of this something very stronger force which is happening inside the proton. So this outside force, that is nuclear force, which you can see, is actually the residue, only a fraction of the force which is happening inside the proton. So some force will leak outside and cause the nuclear force. So that strong force, okay, let's see, there's a atom and nucleus, and the protons or neutrons. So proton and neutron, there is some force in between, inside, something is happening. So the proton and neutron has some internal structure. That means it is made up of something. And that's something we call it quark. So the constituents of the nucleons are quark, which are electrically charged particles. So electron has charged particle, we call it 1e, that is equal to 1.6 10 power minus 19 coulomb, absolute value. So this quark has fraction of that. Some has 1/3 of that, some has 2/3 of that. So we'll come to this point. So proton nucleons have some internal structure, and that is called quarks. And quarks comes in six kind, and they are developed three different time period. So this is called first generation, second generation, third generation. So up, down, first generation, charm, strange, and top bottom. So these names are strange, but these are just a name. They are nothing to do with the up, down, or top, bottom. So up quark, which is up quark is the lightest quark, and after that down, and it becomes heavier and heavier. So mass is about 2.4 MeV, charge is 2/3, and it is a spin particle. It has some spin, which is half spin. Similarly, down is charge is -1/3, spin half, and so on. So 6 quarks. And later on, because of some reason, I'll explain that. Another quantum, another quantity, just like a charge, quarks has charge, spin, mass. So another quantum number is also added because of that. So what happened? We do experiment. We see something. We try to explain. If we could not try explain based on the old theory, then we have to include some more things to explain. So something happened that doesn't explain, and the color quantum number is added on that. So we'll come to that. So what is that means? All these 6 quarks comes in color, different color, and that color means just a name. It is not actual color. So they comes in green, red, blue, green, red, blue. So you have 6 quarks, 3 and with the 3 different color. That means up will be, we have red up, green up, blue up, and so on for all 6 particles. And the Dirac theory also show that every particle has an antiparticle. So these 6 quarks comes with their anti-particle or partners. So anti-up, anti-charm, and so on. So if it is a red color, then the anti-red will be anti-red, opposite of the red. So everything will be opposite. Everything will be opposite. Okay, so 6 quarks, 6 anti-quarks. Okay,
just to clarify, the color code is just for classification. You said that did not actually. Okay.
Oh right, yeah, just a quantum number, just a name is given, just like a up, sorry, somehow it is okay. So just like up, down, it has nothing to do with the up or down or beauty or charm. It's just a name. Similarly, this color code will give the name. Red, green, or blue, it is just a name. So what is the reason behind is that when the particle is formed by combining these quarks, they always form in a colorless form. That means when the quarks combine, they have to be colorless to observe outside. So that's why it's red, green, blue comes. When the red, green, blue are combined, it becomes white. So that is the reason behind that. So it is nothing to do with
down, charm, strange. That's same concept, right?
Yeah, same concept, just a name. It has nothing to do with any up or down. It is just a name. Somehow, okay. 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 So the quark interacts by electric field. So now we have inside the proton. Let's say we have a proton. There are quarks. Okay, we'll see later. There are quarks inside the protons, and these quarks have charge. They are charged particle as well as color particle. Okay, so that means this charge particle interact via the electric field because of the charge, and they will interact via the color force also. So there is a 2 kind of force that quark has. Quark will interact through the 2 kind of forces because of the charge, electromagnetic force, and because they have color, So will comes out that is color force. We call it a strong force. So so inside the nucleus here we have quark, 1 quark, 2 quark, 3 quarks. So they have charge. They have charge, electromagnetic force, and there is another. Okay, so nearby. Okay, let's say another proton. So it has quark, quark, quark. Because of the electric force, they should repel each other, but they will attract each other. Why? Because this force due to the color or quantum number, that is a color force or a strong force, is much stronger than the electric repulsion. Electric repulsion due to the electric force. Okay. So, yes. Okay. So there is two. Quark will interact via two kind of force: electric force as well as color force, color field. However, force due to the color field is much stronger, and that's why these nuclei are bound together. So we go a little bit in detail on that. So the theory of strong interaction, that is because of the color quantum number. So it gives some another kind of force, which is a strong force, and the theory of that is called quantum chromodynamics. Okay, chromo of course comes from the color, and that is come from the general Yang-Mills field theory and developed by Gelmans and so on. So quantum chromodynamics. So electromagnetic quantum electrodynamics, and now comes the quantum chromodynamics because of the color. So color particle, when we have color particle, let's say we have quarks, another quark, they interact via the color force, color field. The exchange particle is called gluon, and there are 8 different kind of gluons, okay, which are zero mass and have no electric charge. And there are 8 different kind of gluons. So they will interact via each other, and the exchange particle is a gluon in this case. Okay, so now if we look on this force, okay, so if I plot the distance in this direction, and that is a color charge, that is a force, let's say, a color force, then if we go closer, let's say we have one proton is here inside the nucleus, another proton is here inside the nucleus. Inside the nucleus, they are held tight together because of the color force. Okay, and let's now go inside this nucleus. Rather than that, let's go inside the proton. There is a proton, so we have a nuclear quarks inside this. So these quarks are held to, they are tight. The strong force is this. Okay, of course, the name is a strong force or the color force. If I try to pull the quark away, it is very hard to pull the quark away because the attractive force due to the strong force is very strong. So it is very hard to pull away. So let's say if quarks are close together. So close together, so there is some color force. So there is some color force here. Distance between these quarks. If I try to pull away, then the force increases very dramatically, very sharp. So very hard to take out the quarks. However, if they come closer together, very close, then the force almost vanishes. The force almost vanishes. And that is called asymptotic freedom. So that means the quarks are free, almost free when they are very close together. And asymptotic freedom, and that freedom, because of that behavior of the quantum chromodynamics, it is possible to use the perturbative theory in the calculation of theoretical calculation. So, and when the quarks comes in the asymptotic freedom, they are very close together, then that state of the matter is called quark gluon plasma when they come very close together. So they are almost free, so they are close together, and that state is called quark gluon plasma. At least, of course, there is some exchange force going on between them. So there is, of course, gluon, and there is an interacting via the gluon. But the force is very small, so asymptotic freedom, not completely free, but almost free. So that state is the quark gluon plasma state, which is of course we call it the fourth state of the matter, and it is assumed that this state of matter existed just after the Big Bang, during the nuclear evolution of the universe, evolution of the universe. So after the Big Bang, there's quark formation, energy, and the quark formation, and at that time there was a matter is a quark gluon plasma. And as the universe cooled down, this matter, quark gluon plasma, they start to form the baryons, some nucleons, and so on. So within few, very small time, just immediately, it formed the quark gluon plasma. That is the assumption. And that is the purpose of the experiment at the Long Island City. There is a Brookhaven National Laboratory, which has a linear accelerator, and in which case, we hit the gold ion. Gold comes from here. Gold is, in this case, gold or maybe platinum, gold or lead or copper, anything. They come at the speed of light and they collide each other. So they form very high dense matter. So that was the purpose of to study the quark gluon plasma. How does it look like? So that was the purpose of this experiment, which is still going on. Now, but actually quark has not been detected separate. We cannot detect separate quark. We can detect proton, we can detect neutron, but we cannot detect separate quark because quark cannot exist separately. So that is so the people give some logic. Okay, quark exists in the colorless state. That means it can. So just like earlier we say the color, red, green, blue. So they exist in the combination of red plus green plus blue. So it makes colorless. So whenever this quark combine to form nucleons, they combine such that it becomes colorless. Otherwise, they have to match the quark such that the whole thing becomes colorless. So only colorless state, quantum state, colorless particle we can observe outside in the detector. The quark we cannot detect inside in the detector. Of course, in the laboratory, when you hit something with very high energy particle, the quark will produce, okay? But that quark will stay for a very, very short time. That cannot go to the detector. That cannot live long for to go to the detector. They combine with other quarks to form the other particle. So here for the proton, up, it is combination of up and down quarks. So two up and one down. So one up is maybe red, another up is maybe green, and another down is maybe blue, or maybe some different color. It does not have to be this color, but it is up, down. So up quark has charge 2/3, up has 2/3, and minus 1/3, so it is +1. And we saw that because we know that we read in the textbook that the charge, elementary charge is 1e, which is 1.6 × 10⁻⁻19 coulomb, but here is a fraction charge. So, but because we cannot observe this quark, so basically we cannot observe this fraction charge also. So what we observe is the whole charge, that is 1.6 and those things. So this quark has fraction charge, but we cannot observe this separate charge, a separate quark. We observe only when they combine to form the nucleons. Similarly, neutron, it is down, 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 up, up, down, down. So it's minus 1/3, that is for the down, minus 1/3 for the down, and up is 2/3, so combine together to form the charge. So they combine to make the colorless three. So proton, neutron are the three quarks. Internal structure, it has three quarks. So the proton mean life of the proton is about 10⁻29 or 30 years. so it is almost stable. Neutron is almost same lifetime as long as it is inside the nucleus. But if you take out the neutron outside the nucleus, it will decay to some other particle within 15 minutes. So it does not stay. It is decay. It decay is split to other particle within 15 minutes. So its mean life is 15 minutes outside the nucleus. So inside the electromagnetic nuclear force, it is stable. So that's why we have a stable atom. But in the laboratory, this quarks, so this has quarks. In the laboratory, we can take out this quark. We can kick the quark outside by hitting with some other small elementary particle. So it is quarks. It is some proton or some other particle. We accelerate some small elementary particles such as electron or proton or some other particle elementary and hit this. If the energy is very high, then we can knock out this quark from this bonding. But this quark ultimately will combine some other quark to form another particle. They do not come outside they do not reach the detector. They cannot reach the detector. So just like in the nature, what part we have in the nature? What we see? Only atom. We see only atom and the photon. That is what we see. Which is a photon. Atom and photon. So atom is stable, photon is stable. That is that photon is light. That is what we see. So atom means it has proton, neutron, electron. Okay. So the proton, electron, neutron. So but let's say we have this proton here. We accelerate an electron, hit with the electron very hard. It knocks out the proton, and it will combine with other quarks inside the other proton. So there is not only one proton, there are many protons. So it combines with other quarks inside the other proton, and it can form some new kind of particle. So when this kind of collision happens, we can collide with some elementary particles, then some new kind of particles produced. So one of them is like a lambda, which charge is 0. It is made up of up-down and a quark called a strange quark. So it is a strange name is because the particle was produced, detected, has some strange behavior, which could not be explained based on the available physics, available theory. So people give its strange name because it is acting strangely. So lambda is made up of up-down strange quark, which is discharge and charge is 0. Lambda mass is like a 115 mega electron volt. So to compare with the mass, we can write the mass in of course we know that we can write the mass in kilogram. We can convert the mass kilogram to the electron volt also. We can write the mass in electron volt unit also. What is the 1 electron volt? Means it's 1.6 times 10 to the power minus 19 joule equal to 1 electron volt. That means, let's say we have 2 plates, positive and negative charge plates. We apply 1 volt potential difference. I put an electron here, then it will get some energy. It will get some kinetic energy. It will accelerate. I apply 1 electron volt, and that energy is called 1 electron volt energy. And that energy is basically equal to 1.6 10 to the power minus 9 in joule. So we can convert this joule as the energy. This is energy. Now, to convert this joule energy to the kilogram, we know from the Einstein equation that E equal to mc square. So energy is in joule, mass is in kilogram. So we can convert this mass to the joule energy. And once we get the joule, we can convert to the electron volt. And electron volt, we can convert to the kilo electron volt, mega electron volt, and so on. So the mass of this lambda is 1,115 15 mega electron volt. For the electron, it is about 0.511 mega electron volt. That is the mass of the electron, approximately. So it is very heavier compared to the electron. So in the particle physics, we can write the mass in kilogram, but very often it is almost usually we write the mass in electron volt, in mega electron volt or mega electron volt or giga electron volt, GeV also. So because of the equivalence relation, E equal to mc square. Okay. So this is the unstable particle. We have a stable particle only proton, neutron, and electron and photon. That's it. So whatever we saw is okay, and there are some other small elementary particles. That's a neutrino that is also stable. So, but for now, what we see is the proton, neutron, electron has a atom, and the photon, that is light. So these are the stable things. Whatever produced in the lab will decay, would break into some other particles, and finally its energy will be absorbed in material, convert to the stable particle. So its mean life of this lambda is 2.6 10 power minus 10 seconds. That means it produced and decay to other particle within this time. So one of them decay is the lambda decay to proton and the pi minus. So within this amount of time, it breaks into proton and pi minus. And pi minus again break into other particles. So its branching ratio means, what is that means? Lambda can break to other particles also, not only this, but other particles. But this is the probability. So it is probability of breaking into proton and pi minus is 63.9%. It can break into other particle also, but they have different, smaller probability. So sometimes lambda break into these, sometimes it will break to other, sometimes break to other particle, but the breaking into this is this much probability. So that is called from branching ratio. So, and the particle that we saw, proton, neutron, and we saw here lambda, they have 3 quarks, and the particle made up of 3 quarks are called baryons. Okay, particle with 3 quarks are called baryons. There are other particles, so we can form what we have to form, what we have to make is, we have to make these 3 must be colorless. That is our restriction. Colorless, must be colorless. So we can make the colors by using only 2 quarks. I can take the up red quark, red, and anti-red. What is the anti-red? Okay, some anti-red opposite of the red. So we can combine these 2 quarks to make the particle also. So if we combine, if the 3 quarks involved, that particle is called baryon. Just like proton is baryon, neutron is baryon. Oh, sorry.
Yeah, Chandra, we don't see you.
Yeah. Okay, so let me share again. It happens. Okay. Yeah. So when I switch to the mouse, and it sometimes happen. So 3 quarks particle is called baryons. Similarly, we can make 2 quark particle, quark and anti-quark, opposite. Up, anti-up, up and anti-down. So quark color is the colorless, of course, and the charge is this is the pi 0, which is made up of 2 pi particles, and this is the pi plus, which is also made up of 2 particles, but this is the same particles. So this is charge is 2/3, this is charge is minus 2/3, and this is 2/3, and this is anti, so it is plus 1/3. Charge of the down is minus 1/3, and the anti-down is plus 1/3. So charge becomes opposite. So this is charge of this is pi plus, so it is pi plus charge. So these are called mesons. That is particle made up of only 2 quarks is mesons. So we have 2 quarks particle, 3 quarks particles. So there are other proposed, and some of have been detected also. They are made up of 5 quarks also. 5 quarks. These are all called pentaquarks. It is a baryon, so but it is made up of 5 quarks, so it is called pentaquark. But some of them, theoretically, it is possible, but some of the pentaquarks have been observed, but some had not been observed yet. That is theory, so that they should exist, but it has not been observed experimentally. Okay. Similarly, so this pi 0 has a mean life of this much, 10 power minus 17, very small. So it quickly decay to the 2 photon energy. So pi 0 decay to the 2 photon branching ratio, that is probability is 98.8%. It decay to the other particle, very small amount of time, very small possibility. So pi 0 go to the 2 photon very quickly within this much time. And similarly, pi plus decay to the within this much time. So its mean life is 10 power minus 8, this much. And pi plus go to the mu plus, this is the mu plus, and this is called neutrino. Neutrino. And every particle has, electron has its one neutrino, muon has its one neutrino. So this is called muon neutrino. So this is called muon neutrino. Similarly, there is an electron has its one neutrino. So whenever produced, when the electron, whenever some reaction happens, then with the electron and the electron neutrino has to be come with that. So yeah, okay. So this is called electron neutrino. Electron neutrino, and this is muon neutrino. And of course, they have an anti-particle also, anti, and this has anti. Okay, and because here mu involved, so it comes with a muon neutrino. If it is an electron, then it comes with a electron neutrino. Okay, so it is unstable particle. So it decay to this particle, this two, within this amount of time with almost 100% branching ratio. So, and the baryons and mesons all together we call hadrons. So proton, neutron, pions, lambda, all are called baryons. Hadrons. So hadrons have some internal structure made up of quarks, 2 or 3. So here what we saw is that 2 force, quarks interact with 2 force, electromagnetic and a strong. It has quarks involved in, comes in 3, we have 6 different kind of quarks with the 3 different colors. And they have corresponding anti-quarks with 3 different anti-colors also. So 6 quarks, 3 color, 6 anti-quarks and 3 anti-colors also. And the force carrier, electromagnetic, it is a photon, and for the strong, it is a gluon. So 1 photon and 8 gluons. There is only one kind of photon, there is 8 kind of gluons. So this is so quarks involves lots of interaction, many things, in the 2 different kind of force and different kind of photon and gluon as a force carrier. Okay, so now there is another force called a weak force. So far we saw electromagnetic force, a strong force. So electromagnetic force we can observe also outside, just like chemical bonding, but a strong force is inside the gluon, inside the nucleons, proton, neutron, we cannot see this. And there is a weak force also, which is also inside the nucleons, inside the nucleus actually. And this weak force is responsible for the radioactive decay. So some particles, some elements decay into emits some elementary radioactive particles such as alpha particle or gamma particle or beta particle. So that is because of this weak force. Weak force caused to radiate, emit, cause the radioactive decay. And in the weak force, we do not go in that detail. The weak force, the carrier of the weak force is the W boson and G boson. So W boson has two bosons. One is plus, another is negative charge, another is the zero, which is called G bosons. Okay. So W plus minus and G zero. So these are very, very heavy particles compared to the group photons and other, compared to the quarks. Okay, so the three forces, and of course we have a gravity. Okay, so gravity is whenever there is a gravitational force between two particles. Okay, so Newton's law simply show that, okay, we have a m1, m2 r square, that's it. Okay, that is a force. But whenever in the quantum mechanics, whenever quantum field theory, whenever there is a force, there must be some particle is being exchanged. So the exchange particle in this is called graviton, which is not confirmed yet experimentally, I think. It has mass 0 and it has electric charge 0. So the force mediating the gravitational force is called graviton. Okay, so electromagnetism is the unified theory of the electricity and magnetism because of the Maxwell. So again, so we have four forces: electricity and magnetism, magnetic, and we have then the strong, we have a weak, and we have gravity, gravitation. So electricity and magnetism are combined together. It is called electromagnetism. Electromagnetism. So it is given by the Maxwell equations. So this becomes one. Now, this electromagnetism and weak force are combined together. That is called electro-weak theory, and that is because of Glasgow, Slam, and Weinberg. So which is called electro-weak theory, of course, the combination of electromagnetism and weak. So they say that electromagnetic force and weak force are not the same thing. At certain energy level, they are the same. They start to behave same. But as you go, as you differ from that energy, the electromagnetic force and weak forces start to behave differently. But at certain energies, they behave same. So that means they are the same force. So that's the unification, electro-weak theory. But there is one thing is gravity. It is very difficult because the gravity, using application of the quantum mechanics in gravity is very tough, very hard. So it has not been done. So if it is done, then probably we'll be able to combine electro-weak theory plus gravity, and they will have a one unified theory that is called theory of everything.
Excuse me, I have a question. What about this? What about the strong force? Is there some theory that unifies the electro-weak theory with the strong force?
No, it is not it. So electro-weak is the electromagnetism and weak, but the strong force it is still not combined with that.
It's not combined. Okay, so.
No, so yeah, so electromagnetism, electro-weak, and there is a gravity strong, and then we have gravity. So gravity is the very tough one. So well, it is not.
Okay, go ahead.
Okay. So So once we combine, if we are able to combine all these electro-weak, strong, and gravity, then we'll have theory of everything. That is one unified theory. So it is believed that it is an assumption that at certain energy level, just like at certain energy level, all the forces behave exactly same way. But as the energy changes, these forces split and they start to behave differently. So that is the unification, that at certain energy level they behave same way. So that is the purpose of the string theory. They try to combine all these forces to make one theory. So, okay. So still it is very far behind, okay? It's still very far behind. String theory is very far behind. There is no experimental evidence, the proof of this. Okay, theoretically it is successful, but there is no experimental evidence. Okay, of course, because of that maybe requires very high energy. So maybe for the future. Okay, now so far we saw that hadrons, which is the baryons and the mesons. And there is another kind of particle called leptons. So in the atom, we have proton, neutron, and the electron. So proton and neutron are the baryons or hadrons. But this electron is called leptons. This is another kind of particle because it has no internal structure. No structure, internal structure it has. Okay, so the particle which has no internal structure, we call it the leptons. It may have charge, it may not have charge. It has charge actually. It has some charge particle plus or minus, and it has no internal structure. It has found so far. So these leptons, just like electrons, they can interact via the electromagnetic force because they have charge. They can interact by the weak force, but not a strong force. And of course, their mass is very strong, so the gravity is not the question. Okay, because the gravity will be very, very small. The gravity does not make any sense on that. So the leptons interact via electromagnetic force because of the charge and the weak force, but no strong interaction. A strong interaction happens only in the quarks, between the quarks. Now let's go to the leptons. So these are the quarks we saw earlier, 4. And leptons, we have electron is one lepton, another is muon, another is heavy, is called tau. So electron is the lightest one, mu is the 200 times, it is heavier, 200 times heavier, and the tau is almost more heavier. So mass of the electron is 0.511 mega electron volt, and the muon is 105.7. It is 1.77 giga electron volt, GeV. So tau is very heavy. So this has charge. So electron -1, this is -1, -1. Spin is half spin. So these have, of course, antiparticle. Of course, electron has antiparticle cause. Okay, so we'll see antiparticle later. So electrons comes with the electron neutrino, mu A, and the mu comes with the muon neutrino. Whenever there is a decay of the muon or the interaction with the muon, then the mu neutron involves on that. If there is an interaction with the electron, then the electron neutrino involves in that. If there is an interaction with the tau neutrino, some decay or something, then there is a tau neutrino happens there. And their mass, few years ago, their mass was assumed to be 0, but a couple of years ago, it is found that they have some mass, very small mass, less than the mass of the electron, very, very small mass. So that very small mass causes a lot of difference, because if they have no mass, that means mu neutrino always remains the mu neutrino. It cannot convert to the another one. But because of the mass, this electron neutrino can convert to the other neutrino, can convert to the mu neutrino, and so on. So, because of the small mass of this neutrino. So, okay, so we have 6 leptons, 3 electron, muons, and tau, and the 3 neutrinos. So 3 leptons, 3 quarks, so 6 quarks, 6 leptons, and gamma is the force carrier of the electromagnetic force. Gluon is the force carrier of this strong force, and G plus and W plus minus are the force carrier of the weak force. So we have these are the force carrier, and these force carriers are called bosons. So these are quarks. So quarks, of course, and so these are the leptons. So these leptons here, these are the 3 leptons. And when you combine all these 3 different ways, these quarks, we form the baryon, hadron, baryons and mesons. They have internal structure. And the force, these are the force carriers only. They carry the force. And there is another particle which observed a couple of years ago only, or detected a couple of years ago, which is called Higgs boson. Higgs boson gives the mass to the particle. When the particle interact, the Higgs boson gives the mass to the particle. So that is another force exchange particle, force carriers. So this is the whole things here so far. We have these leptons, these quarks, and these are the bosons. Force carriers are called the bosons. And all these things comes in their anti-particle also. This quarks comes in anti-quarks, leptons comes in anti-leptons. Okay, so this comes with the anti. So electron, this is the electron earlier we saw, it has charge is negative, tau is charge is negative. And that is also comes with electron plus, that is positron, mu plus, and tau plus. And corresponding anti-neutrino also, electron, mu, and tau neutrino. Okay, so see, these are the, so we can combine all these 3 quarks. There are some restriction, some conservation law. We follow the conservation law. If we combine all these quarks, we can form the different baryons, different mesons, but there is some conservation law that need to be followed. Okay, so fermions, so what we saw here is the 2 kind of particle. If I can focus on the spin of the particle, this quark has a half spin. This leptons has also half spin. Okay, but these bosons have the spin 1, 1, 1, 1, spin 1. And there is a graviton, which is not shown here because it is not detected yet. Graviton has spin 2. Let's call it, okay, so there is, graviton has spin 2. So it has 2 spin. So one thing is, it has half spin, half spin. So that is half integer. And it has even integer. Okay, 1, 2 or something like some integer number. So the particle which has some integer number, of course, that happen to be the force carrier. Those are called bosons. And all these leptons and the hadrons are the half integer particles. Spin is half. So this spin is half. So those are called fermions. So fermion particle has half spin particle. So we can split the particle into 2 kind of particle based on the spin. One is a fermion and another is a boson. Fermion has a half spin, half integer spin, and the boson has even integer spin. So when we deal with the collection of fermions or the bosons, that's like a gas of the fermions. There are many protons in the one together in the one space, in a certain space. Then they have to follow certain statistics that is called Fermi-Dirac statistics. And the bosons, they follow the Bose-Einstein statistics. So what is that? Fermi-Dirac statistics means 2 fermions having the same quantum number cannot stay in the same quantum state. So in the one state, only one fermion, that means if we have 2 fermions, let's say 2 quarks, and they have the same quantum number, same color, same spin, everything, they cannot stay in the same quantum state, same space, occupy the same space. So this is Fermi-Dirac statistics, and in the boson, however, it is they can stay in the same state. So they follow the Bose-Einstein statistics. So, but just introduction. We do not. So based on the spin, we can divide the particle into 2 particles, fermion and boson. So boson happen to be force carrier. Fermions happen to be leptons and the quarks. So here, if I summarize the classification, the matter is the matter we saw is made up of hadrons and leptons. And hadron is basically baryons and mesons, and baryons means 3 quarks. Mesons means quark and antiquarks, 2 quarks only. So we combine all those quarks in different way. There are some conservation laws they have to follow, and we can combine to make some different particles, such as this is proton UED, neutron D, DU. There is another called sigma minus DDS, sigma 0 UDS, and sigma plus and lambda, and there is also called lambda minus, lambda 0, and there is a chi, and so on. So this particle we combine 3 quarks, 2 quarks to make the hadron, and that we follow is called a standard model. So within the model, standard model, we 3 quarks and 2 quarks are combined together under some restriction of some conservation law to make some predict some different particle, and that has been observed experimentally also as described by a standard model. However, the pentaquarks have been observed in some experiment, some of them, and what is actual theory of this color force, that is the quarks, is the quantum chromodynamics, and quantum chromodynamics does not say any restriction on the 3 quarks and the 2 quarks. There is no restriction. Only a standard model say, okay, there is a 3 quark and the 2 quark makes the hadron. But the original theory, quantum chromodynamics, does not allow any restriction. So they have prediction of quantum pentaquarks, and some of them has been observed, some of them has not been, and there is a big discussion. There is a big fight actually in the pentaquark. So sometimes ago, when I was a graduate student actually, some say that one laboratory published that they saw the pentaquark. That pentaquark is called theta plus. And after that, some other laboratory also joined. They say that, okay, we also saw that. Another laboratory also saw that. Okay, we also saw that. We also saw that. Then after some time, one laboratory saw that, okay, no, it was not a pentaquark. It was some fluctuation, something happened, and so that it saw the particle. And suddenly after that, other laboratory also joined. They saw that, okay, we did not see also, we did not see also. So they're following the same line. So one laboratory say, okay, we saw that, and the other laboratory also followed. Then the one laboratory told that, okay, we did not see the pentaquark, there was some fluctuation, something, and other laboratory joining the same. So there was a big fight actually. This was very ugly fight actually. Okay. So now, using some conservation law, so using some restriction of the conservation law, we can combine quarks to make different particles, and that is a standard model which allows 3 quarks and 2 quarks only. But the real standard, it is a model which is based on the quantum chromodynamics. But the real theory behind that is the quantum chromodynamics, which does not restrict the number of quarks. So pentaquarks has been observed and has been proposed also. So now let's focus on the muons a little bit. That was what the topic of the talk next time. So muon is a lepton. So it has a charge. It comes in the both flavor, both charge, mu plus and mu minus. So muon, it has a charge of mass of 105 mega electron volt, which is like about 200 times the mass of the electron. And its spin is half. That means it obeys the Fermi-Dirac statistics. And its mean time is this one, so it decays quickly within this second into some other particle. Here is a particle. Mu minus decays to the electron and the anti-electron neutrino and the mu neutrino, because there is a mu, so it comes to be mu neutrino. It is electron, and a neutrino has to become electron neutrino. Similarly, mu plus decay to the E plus, that is a positron, and the electron neutrino, and the anti-muon neutrino, because there is a muon, so it involves a muon, neutrino, electron, electron neutrino. So this decay is almost 100% branching ratio. That means most of the time, almost all the time, it decay in these particles. Sometimes it is very rare. Sometimes it may decay to the other particles. And this decay, the decay responsible for this decay is a weak interaction. Weak force causes this decay, just like a radioactive decay. In the radioactive decay, just like uranium emits some radioactive particle. So that is because of the weak interaction that is happening inside the nucleus. So that is the responsible. So in this decay because of the weak interaction. And the sign of the weak interaction is that the mean life is larger, 10 power minus 6. If it is a strong interaction, it has very small lifetime. It is I don't know, minus maybe 20 or something like that. Okay, it is very small time. Maybe 20, not maybe 15 or something like that, but it's very, very smaller than that. So if the strong interaction happen in decay, it decay very quickly, immediately. But if the weak interaction happen, it takes some time. It is larger time. So that is the difference in the weak interaction with a strong interaction. Okay, so yeah, we compare with the electron mass. Electron mass is this much. Okay, and 1 electron volt equal to this much joule. And by using this formula, we can convert this kilogram to energy joule, and joule we can convert back joule to the electron volt. And if we divide the electron volt, 10 to the electron volt equal kilovolt, and so on, kilo electron volt, and so on. So because of this relation, we can usually we express the mass in electron volt, mega electron volt, giga, or kilo, something like that. Okay, so this is the basic of this medium, muon. So what is the source of the muon? Muon is basically, it forms because of cosmic ray. Cosmic ray means from the outer space, particles are coming. Most of the particles are some protons or some nucleons. They are coming from the outer space. That is because of some stars. There is a reaction is happening, so it comes from the outside. And when it enters inside the atmosphere, it collides with the atmospheric particle, or this particle decay by itself because they have some certain lifetime. So either they decay or collide with the atmospheric particle, and they convert to the another particle, gives another particle, so that when it enters the atmosphere, it forms a shower, it collides, it makes another particle, then again break into another, so it forms a shower of particles. So shower of particles will come to the, form the shower of particle in the atmosphere. So about 10,000 muons reaches per square meter on the Earth's surface in 1 meter. Every 1 minute, 10,000 muons are coming in as 1 square meter. And for the neutrino, there are more neutrinos every time more neutrino. We all discuss neutrino here, which is a ghost particle. People call it ghost particle because it has mass almost 0, so it moves, it crosses anything without any trace. Even it crosses from, it is Earth, it goes from here and come out from here. There is no trace, nothing happens. So this is ghost particle. So right now, many thousands of neutrinos are crossing our body. Okay, so similarly, okay, so yes, okay. So one of them is pion. So the pion of pi plus pi minus. So pi plus, when it comes to the atmosphere, pi plus decay by itself because it has certain lifetime. It decay to the mu plus and muon neutrino, and sorry, mu1 neutrino. Mu plus and mu1 neutrino. Mu plus and mu1 neutrino, simply pi minus dk to the mu minus and n time mu1 neutrino. So this is one of the source of this mu1, because that is the spions are protons or nuclei are coming from the atom, the cosmic ray. When it comes in the atmosphere, they produce a pion, and pions decay to the neutrino, muons. So muons is basically the source is the cosmic ray. And actually, the muon is detected, discovered in the cosmic ray experiment. So what is cosmic ray experiment is, nowadays we have accelerator. That means we accelerate the electron, we accelerate the proton and allow them to hit each other. They produce particle, and these particles are detected in the detector, and we study that. But some long time ago, we did not have this particle accelerator. So what we do is we have this cosmic ray, that is a particle coming from the outer space. So we, on the mountain, people go to the mountain and place the detector there. And after sometimes this particle hit the detector and show some crash, and study that detector. Basically in terms of photographic plates or cloud chamber, there are detectors on that long time, in that time. So it is discovered in the cosmic ray experiment
So,
by
Chandra, so
yeah.
if we can finish in like 5 minutes because it's getting late.
Yeah, it's almost done. 1 or 2 slides only.
Okay, sorry for
So
interruption.
it is discovered by Anderson and Seth. Okay, so it is the photographic plates. It is cloud chamber. In the cloud chamber photograph. So they exposed the cloud chamber with that cosmic ray. It was discovered in 1934. So here is the one. This line here. This white line. So they observed that there is some crash. These are the crash of the particle. Okay, these are the particles. All particles are going away. So they observed that there is one particle which behaves different than the electron and different than the proton, which curve different than the electrons and proton. And there was a not known particle which can show this kind of property. So they named that particle as a muon. In the beginning they have different name, but later on it is called muon, mu plus and mu minus. So it was observed in the cloud chamber experiment by exposing to the cosmic ray. The cosmic ray particle comes from the outer space, and they show the crash on the cloud chamber. So now about one or two slides about the magnetic moment. So what is the magnetic moment? Basically in the electricity that the SCP 202 or 332, what do you see? The magnetic moment is basically if we have a coil, or let's say if we have a current electron here, electron is moving, then there is a current. Or let's say if we have a coil here, then there is a current I. Then the I and the area of this coil, that is called magnetic moment, which is a vector quantity. We figure out the vector quantity. What is the direction of vector is by using the right hand rule. We place the right hand finger along the direction of the current, and the thumb will give the direction of the magnetic moment direction. So if I place this particle or electron or this coil, current carrying coil in the magnetic field, external magnetic field, it has some potential energy, which is equal to mu dot B. So because of that potential energy, natural state of this object is to come to the zero minimum potential energy. So that's why the object falls to the earth, to the surface of the earth. So if I place in this external magnetic field, it has some potential energy, and because of that potential energy, it tries to rotate itself. It gets some twirls and try to rotate itself to go to the minimum potential energy. So basically, mu try to align towards the magnetic field, external magnetic field. So there's a twirl mu cross B. So so for the quantum mechanics, if I use the quantum mechanics, so for the direct particle means spin half particle, magnetic moment is equal to minus GE2O, and yes is the spin, and the E is the charge, mass, and G is the G factor. That's why in the next talk you saw that G muon. So basically, they are trying to figure out what is the G factor. So for the Dirac particle, it has been projected by the Dirac is equal to 2, and it has comes out to be very close to 2. But that is the classical electrodynamics. Quantum mechanics. But when quantum electrodynamics applies some correction on that, it comes out to be, it has a little bit different correction. So that correction is called anomalous. So that's like an anomalous magnetic moment, which is G minus 2 over 2. What is the difference? That is called anomalous magnetic moment of this particle. So for the muon, it has been measured so far is this much. So it is 10 power minus 10. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 0.00 if I remove this one. Okay. So this is the value. Okay. So people are trying to make the better precision of this measurement. So what is the anomalous? What is the value of the, how far it is deviated from? What is the, this is the measure so far. The source is from the PDG, and people are better precision. So this is the main talk of this next week, the G factor, okay, of the muon. Okay, so thank you very much. So that's it for now.
Well, let's say thank you to Chandra. I don't know, we just like, ooh. I have to apologize because it was longer than we expected, but it was very interesting. Thank you, Chandra. If some of you want to stay and ask questions, and if Chandra has time, we're open for questions. You can ask any questions.
I actually had a few over the course of the thing. So I wrote something down for the